Okay, last little bookkeeping detail we got to keep track of here, and then we're ready to leave episode 7 in the dust. We need to talk about something called overflow. Overflow is what happens essentially when you perform an operation and you don't have enough room to hold your answer in. Okay, I always think about those little cards that they have at restaurants that say, please tell us how we're doing, right? And you can say, the food and the service was on a scale of 1 to 5 or whatever. And then there's a little place saying, how can we improve, right? Well, if they give you a space about that big and you're really pissed because you had a bad experience at the restaurant, you have overflow, right? Because the amount of stuff that you want to put into the answer does not fit in the space provided, right? So it's the same thing here with an addition operation. And when we say the space provided, what we're essentially going to mean is that we're going to take two 1-byte quantities usually, although it could be 2-byte or 4-byte quantities, right? But we're going to deal with just 8 bits at a time. And if it's true that when you add those two 8-bit numbers, you can't hold the answer in 1 byte, then you have overflow. And you undoubtedly remember from school, right, that whenever you have a 2-digit number, say, like 37 plus 18, right? And you add those together, you're going to normally get a 2-digit answer. 8 plus 7 is 15. Greater than 1, 3 plus 1 is 5, right? So you get 55 there. Occasionally, though, you can get a 3-digit answer. If you have 37 plus 88, then that's going to overflow. 8 plus 7 is 15 plus 1, 8, and blah, blah, blah is 12. And that right there is overflow, right? Because I added two 2-digit numbers and I got a 3-digit number. Now, of course, it's all between friends here, and so we'll be happy to let you have another digit if you need it. But when we talk about overflow, we mean that the number of digits of the answer is greater than the number of digits in the individual ones. And by the way, you may have noticed this. I remember the day that I discovered this fact and thought I was real smart or whatever, right? That if you have two 2-digit numbers, 37 plus 89 or whatever, right? And you add those, you're always either going to get a 2-digit answer or you're going to get a 3-digit answer where that guy is a 1. Those are your only two possibilities. You're never going to overflow to 4 or 5 or 6 digits. You're never going to overflow something higher than a 1 here, right, as long as you're only adding two things. And that's because if you have the biggest possible 2-digit numbers and you add those, you're still only going to get 198, right? So same thing is going to be true here, right? We're only going to overflow by 1 bit at a time. Now, how do you detect overflow? That may seem easy because we just saw if you have more bits than you started with, then you have overflow. Well, it's not that easy for 2's complement, right? So let's do unsigned and then we'll do 2's complement. Unsigned is exactly that. If you end up having a 1 coming out of the last place, if you carry out into the 9th digit, or however many digits you're allowed to hold, that many plus 1th digit, then that is considered overflow, right? So if we have an example, let's do 4-digit numbers just to kind of keep it easy. 1011 plus 0011. Let's see if we get overflow here. 1 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. We know how to do this now. 1 plus 0 is 1, and 1 plus 0 is 1. So we end up getting that number right there. And by the way, let's just sanity check it, right? That thing should be 8 plus 2 plus 1, because that's 1 in the 8's place, 1 in the 2's place, 1 in the 1's place, which is going to be 11 base 10. This here, right here, is going to be a 2 plus a 1, which is going to be 3 base 10. So hopefully, if everything works out and the stars are aligned all right, I should get 14 base 10. And do we, in fact, get that? That is going to be 8 plus 4 plus 2, which is, yay, verily, 14 base 10. All right, so our addition worked. But the big point here is that we were able to contain the answer in 4 digits. If, on the other hand, we had said, what's 1011? Plus 1100, then we'd say 1 plus 1, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 0, carry the 1. And that 1 here, that by the way is called the carry out. Kind of sounds like a fast food restaurant or something like that, right? That is the carry out of the last place. And by the way, it's called a carry in if we have a carry into a place, right? So if I had 1111 and 1011, then 1 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. 1 plus 1 is 0. Carry the 1, that right there is the carry in to the last digit. And then 1 plus 1 plus 1 gives us 1, carry the 1 there. That right there is the carry out. Now, that's not going to be very important for unsigned numbers, but that's going to be crucial when we talk about 2's complement, okay? But for unsigned numbers, it's very easy to detect overflow because you end up having a carry out. And if the carry out is a 1 here, that means we overflowed into 5 digits instead of just 4, or in general 9 digits instead of 8 or whatever. And so that's what indicates overflow. And again, we can tell that we have overflow because this answer is bogus. This thing right here, if you work it out, that's the number 15. This thing right here, if you work it out, that's 8 plus 2 plus 1 is 11, right? These are base 10 numbers. And so when we add them, we ought to get 26, right? That's what we would expect if our math worked. But if I just take these digits right there, that is actually the number 10, base 10. Which is obviously bogus, right? 15 plus 11 does not equal 10 in any universe. And therefore, that's what overflow really means. It means the answer is wrong. Now, what we're going to talk about is ways to detect it. And for unsigned, the rule is very easy. If you carry out into the next highest bit, then you have overflow, right? And I'm going to give you guys a rule for how to do that for 2's complement. But I want you to see that really what overflow means is the answer is wrong. And we'll see that with 2's complement as well, right? Here's the rule for 2's complement. It's actually very simple, but it's kind of weird to get your head around. It's not if the carry out is a 1. That's not what indicates overflow. If the carry out is a 1, that's overflow for unsigned numbers. And also for sign magnitude, if you just strip off the sign bit and just add the 2 magnitudes, right, it's the same thing. If the carry out is a 1, it's overflow. But for 2's complement, it's not that. For 2's complement, what we say, if there's the carry out is different from the carry in to the last digit, that's what indicates that we have overflow in 2's complement. Get your head around that if you can. If the carry out is different from the carry in, which means if this is a 1 and this is a 0, we have overflow. That's similar to unsigned numbers. But if this is a 0 and this is a 1, we also have overflow, which is weird. And if they're both 0, we don't have overflow, so that's like unsigned numbers. But if they're both 1, you would think that would overflow like crazy. We're carrying into the last bit and then also carrying out. I mean, it seems like we're overflowing the whole world, but actually, paradoxically, that is not overflow because the carry out equals the carry in that case, and it's only overflow if the carry out does not equal the carry in. Okay, so let's do some examples and we'll see how this works. Let's do an example here where we're doing 4-bit 2's complement. And we know, because we've already figured this out, that the range our answer can hold, right, is -8, -8 up to +7. That is the range of 4 bits 2's complement, right? And we know that the lowest number we can hold is 1000, which is -8. You can flip all the bits and add 1 if you don't believe me. And the highest number we can have is 0111, which is 7. And you can work that out in binary if you don't believe me. Okay, so let's do an example here where we want to add -5 plus -2. Now, before we actually crank through the numbers, let's just sanity check this. Is our range going to hold that answer? And the answer is yes. -5 fits into this range, -8 to 7. -2 fits in that range. And you and I both know that the answer is going to come out to be -7, because that's what -5 plus -2 is, and we're used to dealing in decimal, so we can eyeball this in decimal. That too is going to fit in that range, because that is between -8 and 7. So if this rule works right, we should detect no overflow in this case, and that's exactly what's going to happen. All right, so let's figure it out. -5, how do we represent that in 2's complement? Well, we know it's a negative number, so the leftmost bit is going to be a 1. But what are the other bits? Well, -5 is, let's figure out what that would be, right? We know that it's the inverse, or the negative, of +5. So let's write down +5. That right there is +5. Now, let's flip all the bits and add 1. Flip all the bits, add 1, we get 1011. And that is -5. Okay, great. So we got 1011. Now, let's do -2. What is -2? Well, we know it's a negative number, so we know we're going to have a 1 there. But we got to figure out all the digits. So let's write down +2. That right there is +2. Let's flip all the bits and add 1. flip all the bits, add 1, we get 1 plus 1 is 0, 1, 1, 1, 1. Therefore, that number right there is going to be negative 2. So this is what we're doing here, right? 1, 0, 1, 1 plus 1, 1, 1, 0. Okay, let's crank through the math. 1 plus 0 is 1. 1 plus 1 is 0, carry the 1. 1 plus 0 plus 1 is 0, carry the 1. That's our carry in to the last place. It is a 1. And when we take 1 plus 1 plus 1, we get 1, carry the 1. That is the carry out. So the rule is the carry out the same as the carry in? In this case, yes, they are the same, smiley face. Therefore, that is the right answer, which, if you figure out what that is, you will say, okay, what is that number? Well, it is a negative number. Therefore, to figure out the magnitude, we better flip all the bits and add 1. So let's do that. Flip all the bits, add 1, and we get 0, 1, 1, 1. Now, what is that? That is positive 7. Therefore, this must be negative 7. And yay, that aligns with what we know the right answer is, so this all works. Okay? So we do the addition. We check whether or not the carry in was equal to the carry out. They must both be 1s or both be 0s. If that's the case, we're golden. We just figure out what the answer is, and we know we got the right answer. If they're not the same, if the carry in and the carry out are different, we cry foul and say, whoa, can't even perform this operation. We're going to get something out of range. Okay, so let's see an example where that happens. Let's say we wanted to add negative 5 plus negative 5. Now, just between you and me and the 4 walls, is that going to fit in our range? No, because that answer is negative 10, and we know that our range for 4-bit 2's complement is negative 8 to 7. That answer is certainly not in the range. Of course, both the operands are, but this is an instance of overflow, where we're going to go over because we cannot hold our answer in the range. Okay, so let's see what happens. We have to say, what's negative 5? Well, we did that on the previous slide, right? We said, well, we know it's a negative number. It's the negative of 5. So let's take 5. Let's flip all the bits and add 1. So we say 1, 0, 1, 0. We add 1. We get 1, 1, 1, 0. I'm sorry. No, we don't. We get 1, 0, 1, 1. Therefore, that number right there must be negative 5. So we're going to get 1, 0, 1, 1. Okay. And we're going to add that to negative 5. What's negative 5? We just figured it out. Same thing, right? Now we add, and we say 1 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. 1 plus 0 is 1, do not carry. So the carry in right there is a 0, right? We didn't write the 0 because we don't have one, but if we did write it, it would be a 0. We are not carrying in to the last place. However, we are carrying out of the last place because 1 plus 1 is 0, carry the 1. That guy is not the same as that guy. Not equal. Frowny face. Therefore, this is not the right answer. And of course, if we ask ourselves what that answer is, we say, well, what does that represent? It is a 0 right there, so it's a positive number. What positive number is it? It's going to be positive 6. So what we just concluded was negative 5 plus negative 5 was equal to 6. That is obviously borked, and therefore that is not a legit answer. And what we should do is throw up our hands in despair, and that is exactly what we're doing with our rule here. The rule says since the carry out and the carry in were not the same, that implies that this was not a legit operation. So, as I said, the real meaning of overflow is that the answer is wrong, but the way you can detect that is either for unsigned numbers, if there's a carry out at all, if it's a 1, then we have overflow. That's obvious. That goes back to first grade, right? If we overflow the digit, then that tells you we couldn't fit it in the same number of digits anymore. But then for 2's complement, we have this nutty rule where we say, is the carry in equal to the carry out, yay or nay? And that's what tells us the answer. Okay? See if you get this. Let's do some quick review here. What number does the byte 10000001 represent? Very good. I didn't catch you on that one, right? Answer is we have no idea until we are told what representation scheme it's in. Now, what number does the unsigned byte represent? I'm telling you it's unsigned now. The answer is 129 because we have a 1 in the 128th place. We have a 1 in the 1's place. 0 everywhere else. We add it up, it's 129. Now, suppose I lied. It's not really a unsigned number. It's a signed magnitude number. Now what number does it represent? The answer is -1, because this here is interpreted as the sign bit, and the magnitude of the number is 1, because the other 7 bits obviously make a binary 1 here, therefore the answer is -1. Okay, so I lied again. It's not a signed magnitude number after all. It's a 2's complement number. What value is this 2's complement number? Again, that's the hardest one. The answer is -127. Did you get it? Here's how to do it. We flip all the bits and add 1. So this thing right here is 100001. Flip all the bits, we get 011111110. Add the 1, and we get this thing here. Now again, that is not our answer. That is the negative of our answer. This quantity right here at the bottom that I'm circling, that is a positive number because the 0 is in the the leftmost digit. Therefore, this is a positive number. Positive what? Positive 127. Therefore, this number must be -127. So hopefully you get that logic. That always trips up students, right? Because you get so excited about flipping all the bits and adding 1 and getting an answer that you forget that that answer is actually an intermediate answer towards the final answer. You still have to negative it to get what you started with in the first place. Okay, what about this one? 10110100. What number does that represent? Answer is -76. Did you work that one out correctly? Here it is. We flip all the bits. So if I take 10110100 and flip all the bits, I get 01001011. Then I add 1, and this is going to be 1 plus 1 is 0, carry the 1, 1 plus 1 is 0, carry the 1, 1, we get this thing. And then this is the negative of our answer. What is that number? Well, it's going to be 64, because it's in the 64's place. Plus, not 32, not 16, yes 8, and yes 4. So 64 plus 8 plus 4, I think if you work that out, it'll be 76. Therefore, this number must have been -76. This stuff becomes second nature after a while, but you got to practice with it a little bit. What about this one? What number does this 2's complement byte represent? That one's easier, right? Because it's not negative. So therefore we just say, okay, forget all this weird flip all the bits and add 1 stuff. We're just going to say take the magnitude. And if we take 64 plus 32 plus not 16, not 8, yes 4, not 2, yes 1, we are going to get 101 Dalmatians there, right? So this right here, 101, is nevertheless a decimal number because it's, a little 10 here. So, this thing I'm circling here looks binary as heck. It's all zeros and ones, but that is not a decimal number, or excuse me, not a binary number because it has a 10, and that's how you know that. How do you express the number 16 in 8-bit 2's complement? Answer is 00010000. That's a pretty easy one because it's a positive number, right? So if it's a positive number, that means we simply say, let's compute the magnitude of it. And of course, this number right here with a 1 in the 16th place is how you show 16 in binary. What about -16? Now what are you going to get? And that's going to be 11110000. Is that what you got? Here's how. We start with 00010000 because that is 16. So we know if we want to find out how to express this, we need to take the negative of it and find 16. Now, what is the negative of 16? Well, we flip all the bits to get here. Then we add 1 to that, which results in a bunch of carries and stuff, right? And we end up getting 11110000. Simple as that. If I add these 2 bytes, and I'm going to tell you that they're unsigned, right? So 155 base 10 and 108 base 10, if those are both in 8-bit unsigned scheme, am I going to overflow? And the answer is yes, and you can probably tell that just by looking at the decimal numbers, right? We know we can only go up to 255 in an unsigned scheme. Therefore, 155 plus 100 would give us exactly 255. That's the maximum amount, of stuffing we can get into this pillow. So if we add 155 to 100 and something, like 108, we are definitely going to get overflow. And again, the way you tell that is that we have a carry out here. So if you add 155 base 10, which is this thing, and 108 base 10, which is this monster, and you add all those up doing the appropriate things, you overflow into the 9th bit, therefore it is overflow. And again, that is the rule only because these are unsigned bytes. Now, what if they're 2's complement? I'm going to take 103 and 95, both of which fit in our 2's complement 8-bit scheme, right? Because we can go all the way from negative 128 up to positive 127. Therefore, these addends are both in range. But will I get overflow if I do this? And the answer is yes. And here's why. If I take 103 and 95, express them, then what I do is I add. Now, here's the part that's counterintuitive, right? The carry out was a 0 here. So you might think we're okay, because it's like, hey, great, man, I didn't have to go to 9 digits after all. I'm in 8 digits. But just remember, that isn't the rule at all. For 2's complement, the rule is the carry in the same as the carry out? And in this case, it's not true. We carried a 1 into the last place and didn't carry it out. Weirdly, if we had carried it out, then it would be okay, right? But since we didn't carry it out and we did carry it in, that's what constitutes overflow in 2's complement. Okay, so a lot of this seems like, trivial nutty rules or whatever, and it sort of is, but obviously at the heart of computers, right, are binary numbers, because that's all we can really represent in today's technology is zeros and ones. Therefore, it's extremely important to understand how to perform all these operations. Thanks for hanging in there. Catch you next time on All the